We have seen a number of algorithms for string matching. So we saw initially the brute force thing, then we saw the Boyer-Moore algorithm, then we saw the Rabin-Karp algorithm which transformed it into a numeric calculation. Then we saw the Knuth-Morris-Pratt algorithm which built an automaton of prefixes and did it in a single pass of the text. In all of these, we were looking for a fixed query. A query was a fixed string against a fixed piece of text. Right? So we have a pattern which consists of one word or a kind of set of a sequence of words, and we are looking for a match of this pattern against the text. Now, what if we want to look for a real pattern? That is something which can be matched in more than one way, right? So instead of looking for a fixed pattern, we want to look for a, let me call it a flexible pattern. So for example, supposing you are looking for a name which is spelt differently by different people. So let's say you are looking for the name Srivatsan and you are not sure whether the name is spelt with a T or with a TH. Now you could of course give two sequential queries. You can first look for Srivatsan with a T alone and then look for Srivatsan with a T and an H. But it would be nice if you could express your query as saying look for either copy of this, right? So that is a more flexible search than looking for a fixed string. Or you might have some idea about the beginning and the end but not something in between. So for instance, this very often happens when we are looking for the names of files, for instance, on our computer, right? We want PDF files, so we know that the extension is PDF, and you might remember that you started off the word by saying lecture, so you are looking for a PDF file whose name starts with lecture and whose name ends with PDF, but you don't remember what happens in between. So here is an example. Supposing we want to look for a word that starts with the letters SUB and it ends with TION, right? So this should match a text which has, say, substitution, because this starts with SUB and ends with TION, but also subtraction because this also starts with SUB and ends with TION. So this is a different type of pattern. So the first type of pattern we were looking for is this or that. Either we want Srivatsan with an H or without an H. Here we are saying we know something happens in the beginning and later something happens, and I don't want to describe what happens in between. So what happens in between is kind of left flexible. And finally, you might say that I am not very sure how many copies there are of this. There is one or more copy of it, right? So if I am looking for one or more copy of NA, it would match. It does not match pancreas because there is no NA, that's only an AN, but it does match banana because there are two copies, right? So this is repetition. So we now have this more elaborate notion of pattern that we want to describe. So how would you go about phrasing your question, right? So you want to take a piece of text and you want to tell the algorithm that is searching for it, please find me SUB followed by something followed by TION. How do you phrase that? So we need a way of describing these patterns. So remember that we are always working within the context of a fixed set of symbols, and it's usually a finite set of symbols. So normally the symbols that we can type, for instance, and we said that we will refer to this as an alphabet and we will denote it by this Greek letter sigma. So all our patterns are with respect to specifying in advance the set of symbols from which the patterns can be built. So we can say that the letters are A, B, C or whatever, but they are a finite set of letters. So sigma denotes this finite set of letters which are there in the text and which are there in the patterns we want to build. So when we describe a pattern, then a pattern can be thought of as something which matches a set of words, right? So for instance, the word SUB ... TION matches words subtraction, substitution and so on. So I can describe in terms of this pattern which all words it matches. So a pattern matches a set of words over this alphabet. So now what we will do is we will describe simultaneously how to build a pattern and how to associate with that pattern the set of words that match that pattern. Right? So this will give us a clear understanding of what each pattern means. A pattern, the meaning of a pattern is the set of words that it is intended to match. Right? So the first and simplest pattern is just a single letter. So if I take a single letter A, then it matches the word consisting of that single letter. So A matches A, B matches B, and so on. So in general, a pattern matches a set. So here the set is just got one word, which is the letter A. Now a more elaborate pattern is like Srivatsan with an H or without an H. So if we have one pattern Srivatsan without an H and one pattern Srivatsan with an H, so the first Srivatsan matches a certain set of things, the second Srivatsan matches a certain other set of things. So Srivatsan plus, so Srivatsan with an H plus Srivatsan without an H will match, the documents will match this or that. So that is the union, right? So if I have a pattern P which matches some set, and if I have a different pattern Q which matches some set, then the way I express this union in the world of patterns is to write plus. So if I combine two patterns with a plus, it means it matches the set of either pattern. So either it matches a pattern which with a word which matches the pattern P, or it matches a word which matches the pattern Q. So it matches overall SP union SQ. Then we had that substitution kind of example, right? So we had words which start with something and end with something. So the way we would build that is to say that we first have a pattern for the initial part, and then we have a pattern for the later part, and then we combine these two exactly as we do in strings. We concatenate, right? We have this string concatenated with that string to form a longer string. So we have this pattern concatenated with that pattern to form a longer pattern, and it will match anything whose first part matches P, second part matches Q. So if I have P which matches a set and Q which matches a set, and I take a pattern of the form P followed by Q, I concatenate the patterns, right? Then it will match the set of words which decompose into the first part being from SP and the second part being from SQ. So it will match a concatenated word where I can split the word so that the first part matches P and the second part matches Q. Any word which can be split that way matches the pattern PQ. And finally, we had that banana example. So we said we can take a pattern and we can repeat it, right? So if I write P plus, it means I have one or more copies of the pattern. So if I have one or more copies of the pattern, I know how to match one copy of the pattern, because P can be assumed to already know what P matches. So P plus will match any sequence of words where each of those words matches P. Now P plus is one or more. Usually in this theory of these patterns, you write P star. So P star matches 0 or more. So what does it mean to match 0? It means it matches the empty string. We will talk about it a little later. But there is a technicality. So P star is the usual notation. So P star matches 0 or more occurrences of the pattern. So if there is 0 occurrence of the pattern, then it is empty, right? So it is matched by the empty string which does not have any occurrence of anything. But if it is P plus, it must have at least one copy of the pattern. So with this syntax, okay, which might be a little bit overwhelming. So what we had is we had A, right, and then we had this choice either P or Q. We had this P followed by Q, and we had this P plus and P star which denote repetition, right. So we can now look at some examples just to understand better what this does. So if I look at the pattern A plus B, then it must match the set consisting of the words A and B. And that's because we know that each individual letter matches the set consisting of that letter alone as a single word. So B matches the set B, A matches the set A, and now I have to take the union. So I take A union B, right, and I get the set consisting of two words A and B. So obviously if I do it for two different letters C and D, C plus D will now match the set C comma D, because C on its own matches the set C, D on its own matches the set D. Now let's look at that sequencing, right, concatenation. So now if I take this pattern and follow it by this pattern, so I take A plus B followed by C plus D, then it will match anything which I can decompose so that the first part comes from the first pattern and the second comes from the second pattern. So the first part can be A or B and the second part can be C, or the first part can be A or B and the second part can be D. So if I look at on this side I have A or B, and on this side I have C or D, and I look at all the words I can build by combining this. So I can do AC, I can do BC, I can do AD, I can do BD. So these are all the words I can build: AC, AD, BC and BD. So each one of these can be split so that the first half satisfies P, A plus B, and the second half satisfies Q, C plus D. So this is how we build up patterns, build up larger and larger sets of words that they can match. So now if I take this pattern and now I apply this plus to it, then it will match now actually an infinite set of words, because remember that I can match any word which decomposes into parts which match this. So remember that the words I had were AC, BC, AD and BD. So if I take AC followed by AC, the first AC matches the pattern, the second AC matches the pattern, so AC, AC matches this repeated pattern. Similarly AC, BC matches, similarly BC, AC matches. But also AC, AC, AC matches, because I can have one or more repetitions. So I could have 3 repetitions, I could have 7 repetitions. So there is no limit to this. So once I put a plus, I blow up the set that matches typically into an infinite set. I have an infinite set of words which matches the pattern. Right? So when I start with this single letters, I only have single letters. When I have plus, I only take 2 sets which are finite, the union will be finite. If I take 2 sets which are finite and I concatenate them from every, so I have a cross product in some sense, if you remember this cross product notation, right. So I have everything from one set combined with everything from the other set. So the number of things, so here for instance, I had 2 words and 2 words, so I had 2 times 2 is equal to 4 words, so that's why this has 4 words, right, because it's A cross B. So as long as I am working with plus and dot, I can only build finite sets of words which match my pattern. But the moment I do this repetition, right, then I go outside this finite set and I can now talk about an infinite set of words which matches. So this can be now extended with some shortcuts. So for instance, supposing I want to match an A followed by a B, like we had earlier the string sub followed by TION in between. So what comes in between here is any symbol from sigma. Right? So if I assume that sigma consists of k letters A1 to AK, then A1 plus A2 says either A1 or A2, right? We saw that A plus B is either A or B, the word letter A or, so plus A3 will be either A1 or A2 or A3. So if I write this expression A1 plus A2 plus AK, so if I take the plus and combine all the letters, it says that it will match any one symbol from sigma, right? So the expression, if I take all the letters in sigma and I just combine them into one expression with plus A1 plus A2 plus A3 plus A4 up to AK, then that expression matches one letter, but that one letter can be any letter in sigma. So I will use the word the letters, the symbol sigma itself to symbolize that expression, because it occurs so frequently, right? So it occurs so frequently that we frequently want to say any letter. So for any letter we will use the shortcut. Instead of writing A1 plus A2 plus A3 plus AK, we will just write the word sigma. So now what we want is an A followed by one or more repetitions of any letter followed by B, right? So this is the same as writing A followed by A1 plus A2 plus AK. Remember that it's finite. So A1 plus A2 plus A3 plus AK is a finite expression plus B. So this whole thing I am just collapsing as a sigma, just a shortcut, right? It's just an abbreviation. So this is one way. So this is saying an A followed by any number of letters, one or more, I don't care what they are, ending with a B. And of course, if I don't insist that there must be one or more, and this is why the 0 or more becomes important, I can replace this plus by a star, right? So A sigma star B says 0 or more. I have an A at the beginning of my pattern, I have a B at the end of my pattern, I have something in between, there may be nothing in between also, it could just be AB. So if I say A sigma plus B, then I don't match the word AB, right? AB does not have anything between A and B, so that will not match, so this does not match, whereas this does match here, right? So sigma star is sometimes needed if we want to express the fact that I may have something and I may not have something also. So let's go back to that earlier example looking for Srivatsan or Srivatsan. Now supposing I don't care where it occurs in my text, then I will say that Srivatsan can be preceded by 0 or more letters from my alphabet, followed by 0 or more letters from alphabet. I just want to see in the middle this sequence S followed by R followed by I. Remember that if I give you a word, it is like that pattern A followed by B, P dot Q dot R, A dot B dot C dot D looks for A, B, C, D. So Srivatsan, these letters in that order will match exactly the sequence Srivatsan. So this is one possibility, or I want to find any letters which surround the word Srivatsan with an H, and I want either of these, so I use the plus, right. So this would be the long-winded way of writing this. Now, this matching anywhere in my text, that is putting a sigma star before and after, is so common that this is the default. When we actually use these expressions, these patterns in searching, when we use it in a library like we do have it in Python, as I will mention shortly, then it actually matches anywhere. It's like when we do a string match, right? When we do a string match, we are saying look for the string anywhere in my pattern. Sometimes we say I want all the positions, sometimes I just want to know whether it's there or not. So the default is actually anywhere. So I can drop these sigma stars and write that earlier pattern as just Srivatsan without an H plus Srivatsan with an H. And this pattern will match these two words, either of these two words, anywhere in my text. But now you obviously see that this is a redundant thing, because there is a lot of this which is the same except for this letter H, right? Srivatsan and Srivatsan are the same. So it would be good to say that I have a much smaller difference between the two. It's not Srivatsan or Srivatsan, it's Srivat with an H or without an H followed by San, right. So how do you write that without an H? So without an H means there is nothing there, right. So we need a way of denoting nothing there, and that we use this special symbol, this Greek epsilon, which stands for the empty pattern. So the empty pattern matches the empty string, as you would expect, that is no letters. So now we have a pattern which says start with SRIVAT, right, then either have an H or don't have an H, don't have anything, and then finish with SAN. So now this becomes a more compact pattern which specifies the distinction between these two spellings, right. So there are many different ways to write the same pattern, and depending on how clever you are, you can compress the pattern. But remember that when you write more and more compressed patterns, you need to be able to decode also what this pattern stands for. So writing these patterns and then understanding whether the patterns actually express what you think they are expressing are two different things. So we have now moved to this assumption that when I write a pattern P, it matches anywhere, right. So if it matches anywhere, sometimes I am really interested whether it matches at the beginning or the end. For example, if I am looking for PDF files on my computer, and if I am looking at a listing of all the files, I would like the PDF to be at the end. Similarly, if I am looking for all files which are lecture something or the other, I would like the word lecture to be in the beginning. So sometimes I need to specify this anchoring. The pattern is the beginning, pattern is the end, right. So if I want to write, so this is now an extension of this pattern notation. So the notation varies from one system to the other, but these are quite conventional. So you write this symbol, which it is on your keyboard, you will find this up arrow symbol, which is sometimes used for exponentiation. You sometimes write 7 to the power 6 like this, right. So it's one of the shifted symbols above one of the numeric keys, normally 6. So if I write this before my pattern, then it usually means that I am looking for this pattern anchored to the beginning of my string. So I am only looking for P if it occurs at the beginning of the text. And symmetrically, if I want to find P at the end of my text, then I use the special symbol $ to indicate that P must terminate my. So if you look at an example, for instance, and if I look at this pattern, it's saying B with a beginning anchor matches banana because banana starts with BA. Similarly, NA with an end anchor matches this. Whereas if I ask, for instance, if I said AN $, then though it matches as a string, it does not match at the end of the string. So AN $ would not match banana. So if I want the entire string to match a pattern, right, then I could write that it must start, the match must begin and end. Now this might seem strange to you because it might look like you are actually asking for the pattern to be the string itself, so what does it matter? But if you look at, if you remember my example, right, I want files who start with, file names rather, which start with lecture and end with PDF, right. So my pattern will be something like I start with lecture, right, then I have my sigma star, let us say, and I end with PDF and then $. So this is a typical example where you know what the beginning is, know what the ending is. You want the beginning to be at the beginning, you want the ending to be at the ending, and you don't know what's in between, right. So this is an important case where you actually want to specify both ends. So for example, if I look at BANA dollar, this on its own does not match banana because this matches the beginning, this matches the end, but BANA on its own does not match banana, right? Because if I stop with BANA, then it doesn't match the dollar. It matches without the dollar, you would get it, but with the dollar, you don't get it. But if I put BA and I allow multiple one or more occurrences of NA, then NA matches NA plus. So NA matches NA plus dollar, right? So this matches there. So this works, and therefore this complicated pattern actually matches banana from beginning to end. So what is the kind of rationale behind this particular notation for patterns, right? Where did these plus and this concatenation and the star and all come from? So let's go back to this Knuth-Morris-Pratt algorithm. So while we were explaining the Knuth-Morris-Pratt algorithm, we introduced this notion of a finite state automaton. It was a kind of a special graph where each node represented a prefix of the pattern that we were trying to find, and when we read a letter, we would take an edge labeled by that letter, which will take us from the currently matched longest matched prefix to the next longest matched prefix based on the letter we have done. And of course, if I am going in the right direction, each letter would progress, so the prefix will become longer and longer. And once we finish reading the entire word, that is the prefix that we have read is the entire word, then we will say we have found the pattern. So we will accept this word. Otherwise, we will go backwards, right? We will read a wrong letter and then the prefix we have matched may go back to a shorter prefix. So this is how we process it. So we had this finite state automaton, but it had this kind of a structure. So ideally we are going forwards, right? So we have the first letter like whatever, banana, but then we might come back at some point, and finally when we reach the end, we say okay, right? So it has a kind of a linear structure. Now we could have these automata having branches. There would be more than one way of processing and reaching a terminating thing. So the automaton that we had built for this Knuth-Morris-Pratt explanation has a linear structure, a single path which takes us to the finish line, and everything which deviates from that takes us back along the path to an earlier prefix, right? On the other hand, if you take those graphs, you can actually accept on many paths. So you could have a more general graph which starts at one place and then it allows you, depending on the word, to take different paths. So very much like when we are doing things like suffix trees or something like that, or tries, right? So that is like I start at the top. It's like an automaton, right? I start at the root node and my letters follow a path, and then if I reach the leaf, I accept it. So you can think of that as one version of an automaton. So an automaton could generally have multiple paths and therefore accept multiple words, not just that one prefix I am looking for. So if I look at what kinds of, so each automaton now instead of accepting one word can accept a set of words. So what are these sets of words? Well, they can be formally described mathematically as a particular type of set called a regular set. Okay? And the reason that we are looking at these patterns is that patterns also describe sets of words. Right? So each pattern matches a set of words. So with each pattern I can associate a set. So we have two different ways of describing sets of words. We have automata which describe these regular sets, right? And then we have patterns where each pattern represents the set of words which match that pattern. Okay? And it turns out that this particular syntax that we have used, the particular expressions that we have used for our patterns, right, are precisely capturing the same sets that these automata can capture. So these automata are well studied, so they are a very fundamental idea in computing which go much beyond string matching, and we don't have, unfortunately this is not the course to study it, but hopefully you will study it somewhere. So this idea of automata is very important in order to capture properties of words and strings and various other things. For instance, when we use compilers, a compiler which reads your program and decides whether there is a syntax error is implicitly using a kind of automaton to process your text of your program to decide whether it is syntactically correct or not. So automata are used quite widely. So we have seen one limited use of it in string matching, and now we are seeing a kind of reverse use of it in generating patterns. So the patterns that we can describe using that plus and concatenation and star and so on are precisely those that can be described by automata. And since the automata correspond to what we call regular sets, these patterns, these expressions that we are writing are called regular expressions. So that's where the terminology comes from. So these regular expressions correspond to the so-called regular sets of words accepted by finite state automata. So formally what that means is that if you give me an automaton, any kind of a graph which accepts a set of words, I can actually construct a pattern using the limited operators that we described, for plus for choice and dot for sequencing and that iteration with the superscript star or plus. I can describe a pattern which matches exactly the words which the automaton describes. And conversely, if you give me a pattern, I can construct an automaton for it. So earlier we saw that if you give me a word, I can construct that prefix automaton, but you can do it in a more general setting. If I want all the words which match a pattern, I can actually build it. And then once you can build this automaton, right, you can actually do pattern matching for these patterns exactly as we did string matching in the Knuth-Morris-Pratt thing. So what did we do in Knuth-Morris-Pratt? We built this prefix automaton and then we ran our word through this prefix automaton in one pass. So we got this linear pass where we never had to backtrack because the automaton would cleverly keep track of the longest prefix which has matched. Now you can do the same thing in general for this language of patterns. For every pattern that we can write using these regular expressions, you can construct a corresponding automaton which will process your string in one pass and tell you whether the string that you have got matches your pattern or does not match your pattern, right? So we will not be able to get into the mechanics of how that works because that requires us to understand automata much more deeply than what we have done in this very limited introduction in this week's material. So you can go and look it up and try to figure it out for yourself, but from a practical point of view, what you need to know is that this kind of regular expression matching is available in many programming languages including in Python. So look up the Python library for matching regular expressions, and the syntax that we described here is a very minimal syntax. So Python has and all programming languages that support these regular expressions have an even more expressive syntax for it. So you can describe the syntax in more compact ways. So basically the patterns in more, just like we wrote for example that sigma as a shortcut, right? There are other shortcuts which you can use, and this is very useful when you are trying to look for and process text and look for interesting patterns and find them. So do get familiar with the pattern matching syntax of regular expressions in the Python library and try to make use of it whenever you are doing some non-trivial text processing because it greatly increases the power of the kind of text processing that you can do.